Okay, Duncan, what'd you do?
Uh,
Let's have a look here.
I figured out that 3 to the fourth power is 81.
Okay, here we go. Here we go. Okay, so what do we got here?
3 to the fourth power is 81, and 81 goes into 243 three times.
Okay, good. So this is exactly analogous to what we did with square roots, right? When we simplified square roots. Remember what our strategy was with square roots. If we had something like we wanted to simplify the square root of 50, what do we do? Okay, good. We found the biggest perfect square factor of the radicand, which is what's inside the radical, and that was 25. And so we broke it down into this. Technically, we broke it down into the square root of 25 by 2, and then we split that apart. We never really show that step, but it's there. So we broke it into the square root of 25 times the square root of 2, and the square root of 25 became a 5. And so our goal, we always said, was to write the answer, get as much out of the radical as possible. Another way of saying that is we want to write it with a minimal radicand. We want to get the smallest thing in under the radical that we can. All right, so same strategy here, only this time instead of perfect square, we're looking for the biggest perfect fourth factor of 243, which is 81, it turns out. So we could rewrite this as the fourth root of 81 times the fourth root of 3, and the fourth root of 81 is 3. So we just get 3 times the fourth root of 3. Okay, no big deal. All right, have you done stuff like that before?
No.
Okay,
We could never do that.
I thought for sure you would have, but guess not. Okay, so what about something like this then? What are you gonna do there? Here, stare at that one for a second. Get your bearings, and we'll talk about that one. Now, think about what you would do. Think about this in terms of what you would do if you had a stranded radical on the bottom with a square root, right? Like, what if you got a square root of 5 stuck on the bottom of a fraction? What would you do? Top and bottom by square root of 5. Right? Because you gotta get you have to rationalize the expression, which means we can't have an irrational number on the bottom, right, in the denominator. So we're gonna have to do the same kind of thing here. How are you gonna get that radical off of the bottom? Is Kipling? Is Kipling here?
No.
Okay. Who else is gone? Look around. Who is? Oh, yeah. Okay. So what are we going to do? Any ideas? Is there a way we could rewrite 81?
Yes.
How could we rewrite 81? So okay, so 81 you're saying is we could write that in terms of a small base, right? We could write that as 3 to the 4th. Everybody agree? Okay. So what's that give us then? If we could write this as the cube root of 7 over the cube root of 3 to the 4th, right? In my opinion, it's a lot easier to do these if you think about them in terms of a rational exponent. We don't have to. but we could. So let's think of this, let's just turn this into a rational exponent on the bottom for a second. So how would I write that as a rational exponent instead of a radical? 3 to the 4/3, okay. Now, as long as we have a rational exponent on the bottom that has a non-integer exponent on the bottom, let's say, that's going to amount to a radical, isn't it? Right. So our goal is if we could get that 3 on the bottom, that base to be to an integer power, then we get rid of the radical, right? Everybody agree? While we're at it, let's go ahead and on the top we'll make this a 7 to the 1/3. Okay. What could we do there? How can I get that to a point where on the bottom I have an integer exponent instead of a fractional exponent? What would I have to multiply the bottom by? And the top by too, because I have to multiply top and bottom by the same thing.
1/3.
Say it again?
1/3.
Well, I have to, now remember when I multiply like bases, I add the exponents, right? So I'm gonna have to multiply by some power of the same base, 3, right? So my question is, what am I gonna multiply? I'm gonna multiply by 3 to what power on the bottom, so that I end up with, on the bottom, 3 to an integer. 3/4, 4/3, then I'd end up with 3 to the 4/3 plus 3/4.
2/3.
2/3 would work, wouldn't it? 2/3 would push that up. That's the next available integer. 4/3 is 1 1/3, isn't it? Right. So I want to be able to, if I could add just enough to push that up to the next available integer, then that would work. I mean, I could push it up further, but I don't need to, right? I'm going to have to just end up dividing top and bottom by something then. So if I multiply top and bottom by 3 to the 2/3, what do we end up getting then? On the bottom, I get 3 to what power? I get, yeah, good. I get 3 to the 6/3, which is 2. Okay, well that's just 9, right? So on the bottom, I did my job. I got rid of the exponent on the bottom, right? What about up here though? How do I deal with this? How do I deal with that? I don't really have like bases there, do I? Okay, but what I do have is I have the same number in the denominator of the exponent. Okay. Suggestions? What can I do? I can multiply. If I multiply these straight across, how am I going to do that? What's that going to give me? Because I don't have like bases. Could I write this, and I don't quite have like exponents yet, but if I had like exponents, look what I could do with that. What is, if I have, let's do A times B. So if I have A times B to the M, what is that? A to the M times B to the M. Okay, so those are not like bases, right? But what if I started here and went in that direction? If I had like exponents, I could, in a sense, I could undistribute or factor out the exponent, right? You see what I'm saying? So for example, if I had 2 cubed times 4 cubed, I could just write that as 8 cubed. See what I'm saying? Okay. So could I get these exponents almost look the same? I've just got that 2 on the top. Could I write this guy right here, this 3 to the 2/3, could I write that as something to the power 1/3? What is 3 to the 2/3? How could I split that? How could I write that as something, you fill in the blank, to the 1/3? We'll look at this as a radical, and maybe it almost looks easier, but
9.
how'd you get 9?
Because it's 3 squared.
Okay. Because I could just make this 3 squared to the 1/3, because what do I do when I take a power to a power? You multiply the exponents, right? So I could just make this a product of 2 1/3, right? See what I'm saying? So now if we rewrite that on the top, if we rewrite that as 7 to the 1/3 times 9 to the 1/3, what does that become on the top? 63 to the 1/3. And on the bottom, I've just got 9. So I'm supposed to write that in terms of what? Simplify. So I'm supposed to write it as a radical. So now we've got to turn that back into a radical. What's it look like as a radical? Good. Okay. Make sense? Okay. Let's look at that same problem. What if we had done that completely as just left it in radical form? Because it works that way too. I think it's useful to see it both ways. So what if we had just done this? What if we had just left it like this the whole time? Same strategy applies. What am I going to do this time? What am I going to do this time? How do I think about it? Somebody articulate our strategy here. On the bottom, I want to get a cube root of a perfect cube, right? But 3 to the 4th is not a perfect cube, right?
That's what that is.
It's 81, which is 3 to the 4th, right? Did I do something crazy there? Oh, you thought it was a 34. I got you. I got to make my exponents a little better, I guess. Okay, so there's my 81. I'm just going to do the same thing, right? Whenever I look at a radical and I see that index of the radical is a 3, I'm thinking of that as the denominator of the fraction, right? So I've really got a 4/3 here. So I could just multiply top and bottom by the cube root of what then? Because this is the same thing as 3 to the 4/3. We needed, on the bottom, we need to get 3 to an integer power. So 4/3, if I add 2/3 to 4/3, just like before, right, I'm getting 6/3, which is 2. So that's going to be a 3 squared there, right? So on the bottom, we get our cube root of 3 to the 6th, right? Cube root of 3 to the 6th, which is just 3 to the 6/3, which is 9. But on the top, look what we get. We just get the cube root of 7 times the cube root of, that's just 9.
Hey, how'd you get the 3 squared?
How do I get what?
The 3 squared.
I got the 3 right here, you mean? Because I needed that plus that to add up to a multiple of the denominator, which is 3, right? Because remember, what this is 3 to the 4/3. And so I need 3 to some fraction that's going to make the exponent an integer, right? Because you get that, right? An integer power does not need a radical. But if I have a fractional exponent, that means a radical, right? Okay? Right? So, same answer either way. Take your pick. Doesn't really matter. Yes, sir.
I did it very good.
How'd you do it?
I multiplied the top one by the cube root of 81 squared, or,
Okay, but you're just going to get really big numbers that way.
yeah.
Right. You could. But then you get these enormous numbers and it's hard to deal with those big numbers. Okay? All right. I mean, you could. You're right. Okay, how about that one? Try that one. Same kind of thing. What's probably the first thing I'm going to try to do here?
Support the radical.
Say it again.
Support the radical.
Okay, even before that, I might try to simplify in here, right? But it's not going to work, obviously, right? So I might try to simplify inside the radical. It doesn't work, so then let's split the radical, exactly. suggestions? And what do you think?
Oh, I'm not raising my hand.
Oh, I know, but I'm calling you.
Well. I'm kind of confused.
Okay, so on the bottom, what would that be as a fractional exponent? Okay, be 4 to the 1/4, right? So then I'd have to multiply the bottom by what? 4 to the 3/4. Okay, that would work. That's fine. So there's one suggestion. We'll see if we can make a small improvement on that. So what Emma's seeing here is on the bottom, if I wrote that in as a fractional exponent, that's the same thing as 4 to the 1/4. And so I would need to multiply that by 4 to the 3/4, top and bottom, right? Okay. Is there an easier way to do that though? Slightly.
I got it.
Yeah.
What if you went, 2 to the 4 seconds?
2 to the, you mean, 2 to the 2/4, you mean?
Yeah.
Exactly, yeah, there you go. See, the bottom, the 4 on the bottom can be written in terms of a smaller base, right? And so if I, this is gonna work fine. We're just gonna have to end up, what's gonna happen is if we finish this process, we're gonna end up having to reduce a fraction, which isn't the biggest thing in the world. But I'm multiplying top and bottom by 4 to the 3/4. That's gonna be, what is that? That's the 4th root of 64, right? So that's a fairly big number to deal with. But if we write it in terms of a smaller base, because 4 is really 2 squared, right? So let's take the same problem and let's just rewrite this as the 4th root of 5 over the 4th root of 2 squared, right? Now what do I have to multiply top and bottom by? On the bottom I've got 2 to the 2/4, right? What would I need, Sam, what do I need to multiply the bottom by to get an integer exponent then? 2 to what? No, I have 2 to the 2/4 right now.
Okay, so you have to multiply it by then 2.
2 to the 2/4, right? See what I'm saying? So let's do that. Let's just leave it as a radical this time. So that means on the bottom we're gonna multiply by 2 to the 2/4, right? Which is the same thing as the 4th root of what? 2 squared is what? 4, right? Right? So then on the bottom, we now get the 4th root of 2 to the 4th, which is what? 2. Yeah, right? 4th root of 2 to the 4th, that's the same as 4 to the 4/4, which is, or 2 to the 4/4, which is 2 to the 1. So we got 2 on the bottom, okay? What about the top? Well, top in this case is pretty easy if we write it this way, isn't it? What's the 4th root of 5 times the 4th root of 4?
20.
4th root of 20. Right? You get it? Okay. These are a little harder than the ones, what is it? So these are a little harder than the ones in the book, but I want you guys to, I want you to kind of get used to these, master these a little bit. This is good stuff to know. Okay, let's try one more. How about this one? Okay, try that. Okay, what's different about this one?
It's only square.
Ah, okay, yeah. ideas on this one? Kirk, you got an idea?
First of all, you can simplify the bottom.
Okay, well, how could you rewrite the bottom?
The fourth root of 3 to the third.
Okay, so on the top, we got the square root of 3. On the bottom, we've got 3 to the 3/4, right? Or same thing as the 4th root of 3 cubed. So what do we need to multiply top and bottom by then to get an integer on the bottom? 3 to what power? I'm sorry, say it again? 1/4, okay. So we're gonna multiply the bottom by the 4th root of 3 to the 1, 4th root of 3, same thing on the top. So on the bottom, that gives us what? 3, yeah, we get 3 to the 4/4, so we just get 3. What do we get on the top?
The fourth root of 27.
Oh, okay.
First thing I got,
How did you, that's right, but how'd you get that?
well, you take the 3 to the 1/2
Mm-hmm.
times 3 to the 1/4, you change the 1/2 to 2/4.
Okay, I was curious if somebody would do that. So you could write this as a 1/2 is the same as 2/4, right? So you could rewrite that as 3 to the 2/4 times 3 to the 1/4, right? Yeah, and I'm writing them as radicals, but you understand when I say that's 3 to the 2/4, right? That's kind of are you starting to look at it that way a little bit, right? 3 to the 1/4. That's giving me 3 to the 3/4 over 3, and what is 3 cubed? 27. Right? That works. Another way to do it. We could have also just done this. Those are like bases, aren't they? Right? So in the numerator, let's just deal with the numerator. So the numerator, square root of 3 times the 4th root of 3 is the same thing as saying 3 to the 1/2 times 3 to the 1/4. What do you do when you multiply like bases? Add the exponents, right? So that's the same thing as 3 to the 3/4, which is that. Doesn't matter, either way. Yes, ma'am?
So when you're simplifying the bottom, is it always gonna cancel with just the like base?
No, it didn't the first time, did it? When we did, if I understand your question, like right here on the bottom, we got 9.
Why did we get 9 that time in three?
Because we started off with 3 to the 4/3, right? Which is the same thing. If we wanted to, we could have written that as 3 to the 4/3. We could have just written as 3 times 3 to the 1/4, right? And then multiply top and bottom by 3 to the 3/4. Hang on. I wrote, what am I saying? It was 1/3. Okay, that was backward. Hang on. This is 3 to the 4/3, so we could have written this as 3 times 3 to the 1/3, right? Because that's 3 1/3. Everybody see that? Still, we're going to multiply top and bottom by 3 to the 2/3, but then we just get 3 times 3. What we did instead, which I think is a little bit easier, is we just looked at this as 3 to the 4/3, and we said, okay, we're going to bump that up to 3 squared, which is 9.
Yeah.
Once again, 6 in one, half a dozen in the other, but as you get good at math, you kind of just start to say, oh, okay, well, those are analogous, and so you kind of, I know that seems maybe redundant a little bit, but in math, it's good to be redundant. It's good to see things from different perspectives and to see that it all just kind of comes together, right? And notice that, like, for example, doing these problems, it's, do you get the sense here, and you're going to get some practice with this, but from my perspective at least, sometimes it's easier to work with radicals, and sometimes it's easier to work with rational exponents, and so you want to just be able to go back and forth between the two at will, right? That makes, it's that way like in physics too. Sometimes in physics, when you get into really difficult stuff like in quantum mechanics, sometimes you want to look at it from the one perspective and sometimes you look at it from another perspective and you just kind of go back and forth a lot of times. Whichever one makes the math easier. Okay, how about something like this? Let's look at some variable stuff. Variables are actually easier to work with than numbers, though. I think a lot easier with this stuff because variables, like what if you've got a base inside a radical that's 8? Well, that's you got to think of that as 2 cubed. But if you have a base inside a radical that's a u, well, it's just a u, right? It's easier to work with in many ways than the numbers. Okay, so try that one real quick. Yeah. Okay. Okay, suggestions. Suggestions on this one. What do you think? Tyler, what do you think?
I don't know if this would make it easier, but we could think of the denominator as u to the third to the third.
As u to the what?
Third to the third because 3 cubed is 27.
Oh, thinking of this one or this one? Bottom? U to the third to the third. You mean, well, I don't see how that, I mean, maybe you got something, I'm just not following. Okay, yeah, I mean, this looks like a mess with these radicals. Do you think this is going to be easier with radicals or rational exponents? Probably rational exponents, right? Because I've got like bases here. This is, remember all the stuff we did with properties of exponents a while ago, right? I mean, it's, at the time, they ended up not being a big deal, and you'll recall that too. We only dealt with integer exponents, but all of those properties still apply for fractional exponents, right? So we could do, if I wrote this in terms of rational exponents, what do I get on the top? What's this? What's that?
U to the 27 or 14.
What's that?
U to the
3 sevenths. Okay, what does our property of exponents say about multiplying and dividing like bases? When we multiply, we add and subtract. Well, we add, right? When we divide, we subtract. So how could I write this in terms of, how could I write this as u to just some power? It's going to be u to what power? The 1/2. What's that going to amount to? U to the 1/2 times u to the 27/14 is u to the, how'd you get that?
I turned 1/2 to 7/14.
Okay, so you're adding, good, you're adding exponents. So you said 1/2 plus 27/14. Now we're going to divide by u to the 3/7, so we subtract, right? When you divide like bases, you subtract. So I just have to simplify that fraction. Well, what do we get? So 14ths would be our common denominator, so I get 7 plus 27 minus 6, so 28/14. Everybody agree? So that's just u to the 28/14, which is what? U squared. Right? That's pretty, I mean, that's a lot easier to me than those last ones. We got like bases the whole way through, right? Just turn it into fractional exponents, use your properties of exponents, see what you get. How about, we're about out of time, we'll do one more if we can. What about something like this? What could I maybe do with that? What am I gonna get on the top? Ruby, what am I gonna get on the top if I write that maybe with just, how about if I write it with rational exponents? X to what power? So on the top, I've got the 6th root of x to the 11th. So where's the 11 going, the top or the bottom of the fraction? Top. 6 goes on the bottom, right? So that would be then x to the 11/6, y to what power? 10/6, okay. And if we want to, we could reduce that to, what would that be, 5/3? Oh, you're right. Okay, what about the bottom? What do we got on the bottom? X to the 9/12, which would reduce to the 3/4, but let's go ahead and reduce it, being as we're going to have like bases, we're going to be subtracting. Let's just get common denominators in our exponents. So 9/12 would be, actually, I can't write that in terms of 6, can I? Can't. So I'm going to get, so we'll just leave it as 9/12, how about? Because we're going to have to make that 2/12, right? What about this one? 10/12. So that would be, what, 5/6? And now what? I've just got pairs of like bases that are being divided. So in my mind, at least, I could divide this up into parts. I could do that part and this part, right? What am I going to get from the red grouping? 11/6, that's 22/12 minus 9/12 is what? 13/12, okay. So I get x to the 13/12 times y to the 10/6 minus 5/6 is 5/6. So it wants me to write these as radicals. So what's this one going to be? 12th root of, okay. Okay, we'll say it again. They'd both be, yeah, there's no denominator. Yep.